We will continue now with hypothesis testing on the 10 steps and look more in depth at steps 4 through 6. The essential questions are: what is phase 2? Within phase 2, what are steps 4, 5, and 6? What is random variation? How can random variation affect your results? What is alpha? And what is our decision rule? A review of the full 10 steps. We've assessed steps 1, 2, and 3 in depth under phase 1. And now we'll look at phase 2, deciding how to answer the question. So now that we have stated the question and have statistically defined the question and have looked at our data and reviewed the assumptions associated with our sample data, how do we actually decide an answer to the question that we formed in step 3? A quick review of the null and alternative hypotheses is that we will define two states and use our data to make a decision between these two states. The null hypothesis is what we currently believe. It's the status quo. It's that there's nothing new going on. The alternative hypothesis is our research question. It's what we hope to show. We hope to show that there is something new that we've learned from our data. A couple of important features of the hypotheses. It is very important to note they are mutually exclusive. That is, only one of these hypotheses is going to be true. We'll assume that the null hypothesis is true and choose to believe the alternative based upon evidence in our data. There are a number of ways to define the hypotheses. On the left, we have the null hypothesis, and on the right, we have the alternative. So a simpler model versus a more complicated model. So no treatment with ECMO would be the null hypothesis, or the alternative hypothesis would be that ECMO, while more expensive and complicated, is actually better for survival rates. The null hypothesis always contains the equal sign, so no difference, no change, no relationship. The alternative always has the difference, so greater than, less than, different from. We have a relationship with ECMO and survival, or we want to change our minds and say that ECMO is better than doing nothing. The null hypothesis would be nothing is happening, that any departure from what we assume is due to random variation, whereas the alternative hypothesis is that it's very unlikely that random variation would give us this observed data. We are going to fail to reject the current state of the null hypothesis, or we're going to reject the current state and accept the alternative state. We'll believe the null hypothesis if our p-value is large, and we will believe the alternative hypothesis if the p-value is small. Statistically, this is very important, we will continue to believe the null hypothesis until we are given enough evidence to adjust the status quo and believe the alternative hypothesis. It is the preponderance of evidence that we are using our data to determine if we can choose the alternative over the current state of the null hypothesis. So phase 2 will decide how to answer the question. So we'll consider all the outcomes that could happen and assess the impact of random variation. So that brings us to our hypotheses for our ECMO study. We have two options for the null hypothesis: that the true percentage of surviving ARDS is less than or equal to 44%, that's a percentage, or that the true proportion surviving is less than or equal to 0.44, that is a proportion. We can actually address the question using a percentage, but statistically it's easier to utilize the proportion and they have the same interpretation. So our null hypothesis is going to be stated as the true proportion of survival from ARDS is less than or equal to 0.44. And our alternative hypothesis will be that the true proportion from ARDS that survive is greater than 0.44. That's our alternative hypothesis. So we need to decide on a summary statistic. In ECMO, our summary statistic is P, the proportion surviving. We currently believe that to be 44%. Therefore, if the null hypothesis is true, we expect our P naught, or the hypothesis of our null proportion, to be 0.44. Keep in mind, in our data, we observed a proportion of 0.663. So we believe it to be 0.44, though we have observed 0.663. That leads us to determining how random variation could affect the observed statistic. If we assume, like we do, that ECMO intervention is no different than the current intervention for ARDS, and that the true proportion surviving really is 0.44, we need to ask ourselves, what survival proportions would we expect to observe if our null is true, and we repeated the study over and over and over again? This is the idea of reproducibility. This is why it's important to understand where your data came from, how the observations were collected, how the outcome is collected, and to have the outcome collected without bias. Your study is only one possible study that could have been done from this population, and we need to understand that if the study is done over and over and over again, what are the proportions that we would likely see? So to do this, we're going to do a little simulation. A simulation is where you take data from what you assume to be true, in our case, a chance of 0.44 survival, and we're going to create data. We're going to create data 1,000 times. Each time, we're going to create 90 participants. We want the study run 1,000 times, and each time the proportion surviving is 0.44. Remember, this actually goes back to your distributional assumptions, and this is coming from a binomial distribution, and it's part of a Bernoulli process. So each individual person has a 0.44 chance of survival. We're going to look at 90 participants, find out how many of those survived, and then we're going to do that 1,000 times. Each time the study is done, we will see a different number of survivors. It's unlikely if we did this 1,000 times, we would always see 41 survivors. We could see 40, we could see 43, we could see 52, we could even see 11 survivors. Therefore, the estimated proportion of surviving is going to be different in each of our simulations. What we actually observed in this study is just one possibility out of a number of possibilities of what we could have observed. So if it's easier to think of it in terms of flipping a coin, imagine a coin that is actually an unfair coin. So heads are going to come up 44 times out of 100, and tails are going to come up 56 times out of 100. We're going to put 90 of those weird coins in a bag, and we'll shake up the bag. Then dump out the coins onto a table and count how many come up heads. Remember, we expect to see 44 heads out of 100. But given the way the bag has been shaken and the coins have fallen, we may not always get exactly 44 of 100 showing heads. If each coin represents a person and each head represents the person surviving, the bag of coins dumping out on the table represents one performance of our experiment, one realization of that proportion of survival. Then do that 1,000 more times and record the survival rate for each of the 1,000 experiments. Now, thankfully, we don't have to actually do this with coins and throwing them on a table and shaking up a bag. We don't even have to actually write this down. Thankfully, our software can do this for us. So, what I asked JUMP to do was for 90 observations with a survival rate of 0.44 to produce 1,000 random samples of survival rates. This is the table, or part of that table, of 1,000. So you can see in experiment 1, 39 people survived out of the 90, and that gives us a proportion surviving of 0.433. So this isn't out of 100, this is out of 90. 90 was how many were in the Peak et al. ECMO group. I've asked JUMP to do this 1,000 times. And you can see here on the left the first 10, and on the right the last 10. In experiment 1, the survival rate was 0.433. In experiment 2, it was much higher at 0.578. All the way down to experiment 1,000, where the proportion for the 1,000th experiment was 0.467. Interestingly, if you notice experiment 992 there, the second row from the top on the right side, had exactly 40 surviving, with the proportion surviving of 0.444 by chance. That's actually relatively close to what our null hypothesis was of 0.44. If you rounded 0.444, you would get 0.44. So we did see here, just in one of our 1,000, something very close to what we expected. If we put these in order, we can actually see how many of each number surviving we saw within our 1,000. So again, on the left is the lowest number surviving of 27. That only happened once. That's a proportion surviving of 0.3. So that's where I took my bag of coins and I dumped them on the table, and out of 90 coins, I saw 27 heads. All the way down to experiment 153, where when I dumped my bag of 90 coins, I saw 55 heads, or 55 survived, for a proportion surviving of 0.61. So you can see that 27 only happened once, but 28 happened 1, 2, 3, 4, 5, 6, 7, 8 times. 55 only happened once, but 53 only happened 3 times. So now it would be nice to know to actually determine how many times each number of survivals occurred out of 1,000. That will give us some estimate of the variability. We know that our proportions range from 0.3 to 0.61, but we also know that not all values occurred in the same frequency. This is actually what the distribution of proportions looks like. So you can see the proportion surviving on the x-axis, and on the y-axis, it's the number of experiments that had that proportion surviving. So remember, all the way on the low side, there was only one experiment with 27 survivors, and that was a proportion of 0.3. You can see that little 1 there, right above the 0.3 on the x-axis, all the way on the left. If you go all the way to the right, you can see that one occurrence of 55 people, or a proportion of 0.61. And then in the middle are all the options that we have. What you may notice, and what you may recall from the lecture on distributions, is that with large sample sizes, the Bernoulli process or binomial distribution begins to actually look a lot like a normal distribution, that bell-shaped curve. However, we do see a little bit of a drop in between the 90 and 100 times, with a low 69 there in the middle. But it really does have an overall bell-shaped curve. So how different is this from what we would expect to see? Well, most of our responses ranged there in the middle from 0.4 to 0.489. That's actually very close to 0.44. So let's take a closer look at the variability. Here we have the same graph displayed 3 times. In the upper left-hand corner, you can see the 2 bars that are immediately about the center of the distribution. Most common proportion is the 100 observations that had 0.456 as the survival rate. But that's only 10% of the time. 32% of the time in the upper right-hand graph, we see 4 lines about the center. So 320 of the 1,000 observations occurred with the survival rate between 0.433 and 467. If you expand that plus or minus 1 more bar on either side of the center, you can see 46% of the time we saw survival rates between 422 and 478. It is interesting to note that only 69 out of 1,000, or 6.9% of the simulations, had 40 out of 90 surviving. That was our 0.444, or rounding up to be 0.44. So only 69 out of the 1,000 simulations did we see a number that matched or closely matched our null hypothesis. So what do we do with this information? If we think about the number of observations or experiments that had a survival rate more than 0.444, our middle there to the 69 bar, the 100 or larger, we see actually that in 45% of the experiments, the proportion surviving was actually larger than our null hypothesis. So clearly, you can see survival rates that are larger than 0.44. It's not uncommon. So what does this mean? We have 2 choices here. the survival proportion is less than or equal to 0.44. To choose this, we're going to say that an event occurred that is within what we'd expect if the null hypothesis was true. Remember, our null hypothesis is H naught, that P naught is less than or equal to 0.44, that our null hypothesis is a 44% survival from ARDS. Our other option is that it's larger than 0.44. That was our alternative, that the survival with ECMO is greater than 0.44. To choose this, we're saying that our observed data, which was 63.3, is compelling evidence that the null hypothesis is not true. 63.3. So how do we make our choice? Well, after observing only 41 survivors, it would be extremely difficult to defend choice 2. We can't just observe a proportion that's larger than 0.44 as evidence that the real proportion is larger than 0.44. Observing 0.456, the bar immediately to the right of 0.44, clearly supports the null hypothesis still. However, we observe 57 out of 90, or 0.633. So how can we leverage this simulated data to make a real statistical decision? And that gets us to stating our decision rule to answer the question. Which outcome leads us to retain our preference for the null hypothesis? Which leads us to conclude that the alternative is compelling. We can't simply go on site. Just because we observed something larger doesn't mean it really is. So the answer to these questions is what we call our decision rule. It is the rule that is going to help us determine which hypothesis to choose, the null or the alternative. If we look at our cumulated outcomes here, so this is a slightly different way to look at the data, the x-axis is still the same, but the y-axis now shows us the number of experiments that had that result or more extreme. So you can see all the way on the left, our lowest proportion surviving, all of the outcomes were 0.3 or higher, so the bar is at 1,000. We only had one outcome with 27 people, so the next bar shows us that 999 of the experiments had something higher than 0.30. If you go through the middle here, you can see that we have 517 out of 1,000. So 51.7 saw a proportion of 0.456 or more. 52 out of 1,000, or 5.2%, saw a proportion of 0.533 or more. And all the way on the right side, we see 1 in 1,000, or 0.1%, that saw a proportion of 0.611 or higher. Now remember, we observed in our data a proportion of 0.633. Our simulation didn't observe anything that high. So what we observed in our data was actually very far away from what we expected to see based on the simulation. So if we observe the P of 0.456, we would likely retain our preference for the null hypothesis. It's very close to 0.44. How far out do we have to go before we believe the alternative? And this introduces a new term for us, significance. What is significant enough for us to choose the alternative that our proportion of survival using ECMO is greater than 0.44? This leads us to another new term called alpha. It's the Greek symbol for the letter A, the lowercase a, script A. It is the probability of rejecting a true null hypothesis. So if our null is true, what is the probability we choose the alternative hypothesis incorrectly? So this is very key to what we will do all semester. Let me restate that. Assuming the null hypothesis is true, what is the probability we will reject it incorrectly in favor of the alternative? That's our alpha level, and we need it to be small. We don't want to make that error. If the null is true, we want to keep with the null. The most frequent values are an alpha of 0.05, of 0.01, or 0.10. Those are standard across the statistical field. We usually utilize 0.05. And what that means is 1 out of 20 times, or 5% of the time, we're okay with going with the alternative when the null is true. The researcher is going to choose this risk of error. They're going to select their alpha. It's also called a type 1 error. And again, it is concluding that the null hypothesis is false when it is really true. How do we choose alpha? The researcher is going to choose this before conducting the analyses. The reason that before is bolded and capitalized here is this is incredibly important. It is called an a priori decision, or a decision made prior to looking at your data. The reason that we select it before we look at the data is so that it is clear in your mind and in everyone's mind that's going to read your research that you didn't cheat. Look at your answer first and decide that I like it enough that I want it to be significant, and so I'm going to select my alpha level to be just a little bit bigger. Our significance level is the proportion of the time when the researcher is willing to conclude HA even when HO is correct, or declaring a difference when there really is not a difference. Remember, regardless of what we're testing here, H0 is what we currently believe. Changing to operate under HA has some cost associated with it. That cost could be monetary, it could be a policy implementation, it could be an expensive drug, it could be exercising more frequently. Anytime you go from H0 to HA, there's cost associated with it. So we would like significant evidence to choose HA, assuming that H0 is true. Like significant evidence for that. And that's where alpha comes in. We choose that before we actually look at our data. So if alpha is small, or 0.05%, if our p-value is greater than alpha, we're staying with the null. If it is less than or equal to alpha, we're going with the alternative. And that means we're willing to say that 5% of the time we're going to choose the alternative if the null is really true. So we're going to make an incorrect decision 5% of the time, but we're okay with that. We set that level before. In the ECMO study, we are going to base our decision rule on the simulation because that's all we have right now. So our null hypothesis was the population of survival is 0.44. And we're going to stay with this if the observed proportion is 0.543. 48 survivors or less. Our alternative is the population survival is larger than 0.44. And we're going to choose that if the observed proportion is greater than 0.543. So 49 survivals or more. Why is that? How did we come to that level? If you take a look back at the descending cumulation of our experiment, if we usually use an alpha of 0.05, we need to find the point where less than 5% of the results are remaining. That would be 50 out of 1,000. We actually don't have that number. We have 52, and then the next one is 35. Well, 52 is actually 0.052 or 5.2%, and that's bigger than our standard alpha. So we have to go with the next lowest cutoff point, which is 35 out of 1,000, or 0.035. You can see here the highlighted bars to the right of 52 are those bars that have 35, 25, 20, 9, 4, and 1. So our null proportion, or our null hypothesis, says that the proportion is 0.44 or less if our observed proportion is less than 0.543. That's our 48 survivors. And then the population proportion is larger than 0.44 if the observed proportion is greater than 0.543 or 49 or more survivors. So we are looking for evidence that falls to the right side of that 52 bar. So anywhere from 35 or over, and that's a proportion of 0.543 or higher, will give us evidence to the alternative. Are we going to make our decision? Not quite yet. In this section, we've reviewed phase 2, which is deciding on a summary statistic. So we're using proportion P for categorical outcomes. Remember, it's important to distinguish between the proportion P and our p-value. So our p-value will be compared to alpha. Our proportion is what we're testing. How could random variation affect that statistic? So if our observed proportion is close to our assumed, so if what we saw is close to what we assumed in our null, then we expect to see small amounts or small variability away from the null hypothesis. We will then state a decision rule using the statistic. We're going to use alpha. We'll choose H naught if our p-value is large or if it's larger than alpha. We'll choose HA if our p-value is small or if it's less than or equal to alpha. Up next, we'll see how to actually use our alpha value to choose between H naught and HA, and we'll complete the remainder of the 10 steps.